let's take a look. Let's go through the functional groups that are interesting to us on an IR spectrum. Let's start with alkanes. The plain old sp3 CH bond in an alkane happens just below 3000. So 3000 is a very important dividing line in the type of CH bonds. So lower than 3000 are sp3 CHs, where the C's are single bonded. Okay, greater than 3000, right? Like just above 3000 up to 3100 are sp2 CH bonds. So compare this spectrum where they're all sp3 with this one. Draw that dividing line. We actually see a pretty clearly defined peak where there is an sp2 CH bond here close to 3100. Sometimes a CC double bond can be apparent somewhere in the middle of the 1600s. So 1640 to 1680, that absorbance can be observed sometimes. Alkynes, we'll keep moving up here. Here's an sp hybridized CH bond right here, well above 3000, way up at 3300, a very sharp resonance there, way above the 3000 borderline. A CC triple bond, 21 to 2200, right there. But this is only if the molecule is not symmetrical. Okay? A symmetrical CC triple bond will not show up. That's due to a little more complicated interaction where the molecule's dipole moment has to be changing in order to actually see an IR absorption. So, for instance, if we had just acetylene, we would not see a CC triple bond. But molecule like this, where it's asymmetric, I have several carbons on one side and a CH on the other side, we do show that resonance here at 2200 or so. And of course, the SPCH only occurs on a terminal alkyne, where the C triple bond C can be shown in an internal one, although it'll be much stronger if it is a terminal one because it's much more asymmetric that way. Aromatic compounds that have a benzene ring to them, show some specific resonances. You can see a sp2CH, just like an alkene, above 3000. That's often pretty weak and pretty tough to see. One of the big giveaways for an aromatic compound is a series of peaks somewhere between 17 and 2000 that are weak. So all of this stuff are the aromatic CC frequencies. One interesting thing that I will show you, though, is that in the fingerprint region, there are normally very characteristic sets of absorbances that can actually show you what the substitution pattern is on a benzene ring. So I have some just for examples. These are all di-substituted benzenes. So a 1,2 di-substituted benzene is where I have two substituents right next to each other. Absorbances around 1150, around 1050, and 750. So this is 1000 on all of them. It's a little hard to see, but 1,3 means there's one carbon between the substituents. 1,4 means they're opposite each other. The 1,3, 1100, 900, 800, and 700. So plus or minus 20 or so, maybe. 1100, 1000, and 800 are important for that one. This one doesn't really count. But if you're pretty confident you have a di-substituted benzene, you can look carefully down in this region and you can figure out where your substitutions are. So this is an aromatic compound. We can tell because of all the garbage that's happening in here between 17 and 2000. We've got some sp2 CHs right here because they're just a little bit above 3000. And then we've got some substitution pattern stuff going on here. This looks like about 1150. This looks like 1050. This big one, 750. Right there. That's characteristic of a 1-2 dye substitution pattern. The IR usually doesn't tell us very well what actually is attached there, but we could get some information from the mass spec. For instance, if they were chlorines, there would be a specific isotope pattern at the molecular ion. Same if they were bromines, right? NMR would be able to confirm the substitution pattern for us based on the multiplicity and the number of hydrogens within the spectrum. Also, the carbon spectrum could tell us if by symmetry the two groups were the same or not. So you don't need to memorize any of this sort of stuff. You'll always have a table to look these things up. And I show you this, for example, because the lab that we're going to be doing that involves a nitration reaction will actually be able to use the IR, hopefully, to figure out a little bit something from that. If not that one, there's a lab in the couple weeks later. So we actually will be able to take advantage of this in order to characterize an aromatic compound. Alcohols are usually a dead giveaway on infrared spectrum because of a large, very broad peak above 3000, right? Maybe centered at 3400 or 3300 or something like that. So it's broad because OHs are constantly exchanging and hydrogen bonding, so there's lots of different formats that OH bond can show, as opposed to a different bond which always has one specific configuration and is always vibrating the same way. Now, one thing to watch out for is that in certain types of ATR, like the ones that we have, the peaks above 3000 will be much less strong, much weaker than what we see in our references. So alcohol peak might look, just something like this if we were doing it on our ATR. And those might still be big like that, but be aware of that sort of thing, that even a peak that's little like this can still refer to the OH stretching in an ATR instrument. That's just because the crystal that's used on the ATR is opaque to infrared in certain frequency ranges. Means have a similar sort of broadened peak above 3000 here, but amines are interesting because that broad peak will have a little spike on it. And the number of spikes shows you how many hydrogens are attached to that nitrogen. So the one spike to it is something like RNH with an R. Okay. One peak comes from one nitrogen. It's that NH stretching frequency right there. Right here, two peaks might come from something like this, RNH2, where one of them is one of the NHs and the other is the other NH. There's sort of restricted rotation, I guess you could think of it as, around that NH. So those two bonds are actually slightly different in the molecule. It's one way of thinking of it. But you ever see something like that that's broadened but has the little bits to it? That's probably an NH. And again, with ATR, these are going to be significantly less above 3000. So be careful with that. ATR, like the instrument that we have. Carbonyls, like I mentioned before, are very characteristic key pieces of important information we can get from an infrared spectrum. So our baseline will be acetone. This is characteristic of just any kind of normal aliphatic carbonyl compound. So I've got a C double bond O in the middle, no other CC double bonds, just all CC single bonds with that CO. So 1715 is sort of our standard default carbonyl frequency. So let's make a little diagram down here, right? Just for a regular ketone, 1715 is our starting point. If I have a ring with any amount of strain to it, that will make it vibrate faster. Okay? A strained ring, you can sort of imagine putting some strain on it, on that bond. It makes vibration happen faster. So we can get things way up in the upper 1700s, even closer to 1800 if I get a even more strained ring than that. Six-membered rings are not strained, remember, so six-membered ring will just be our standard 1715. Now here I have a CC double bond in conjugation with the CO double bond. Okay, it is here. If I actually draw this structure for you, be a little easier to see. I have double, single, double. We've talked about that arrangement before, and we'll talk about that a lot in the next chapter, but that's conjugation. And what happens when it's in conjugation, there's actually a little less electron density in here because it's shared throughout this entire system. So that bond has actually become weakened a little bit, and so it goes slower. And it's actually fairly consistent going from my standard carbonyl to the slower conjugated one. It's a difference of about 25. So let's say minus 25 approximately for a conjugated. Something like that. I plan on taking around 25 off. And these numbers I'm going to give you, these are all good, probably plus or minus 5 or so. I mean, they're that precise, it turns out. Next to this benzene ring, this is also conjugation, right? Because it's double, single, double going right in. So you can tell that those numbers are the same for those. Moving to aldehydes, we tighten the bond up a little bit by a pretty predictable amount. Again, I'm going to add about 15 to that. Here's a regular aldehyde. Here's a conjugated aldehyde. Notice we added 15. So let's go this way. Plus 15 for an aldehyde. For an ester, it's a little more yet. It's about 20 that's added to it. With an ester, there's a resonance structure where those lone pairs from oxygen can feed in a little extra electron density to that CO double bond. So it's actually strengthening it and making it vibrate a little bit faster. A conjugated ester, since the ester brought it up itself and conjugation brought it down, we're back to our baseline number. So I've got two sort of competing interests, and plus or minus 5 anyway. If I have an ester adding to it, if I have conjugation removing from it, we're back to our sort of original number. So as long as you can remember, I don't think you need to memorize numbers too much, but as long as you can remember that conjugation will lower the frequency because that's taking electron density away. Aldehydes and esters increase the frequency, where the regular ketone is just our original baseline number. Finally, carboxylic acids, C double bond O, OH, will show two characteristic absorbances. Of course, there's the C double bond O that's going to be in the normal range, I guess, just a little bit above 1700. The OH will appear, but not like an alcohol. It'll appear as an entire broadening of really the whole region between say 3500 and 2800 or so. So don't look for a specific little alcohol broad peak right there. Look for broadening of that entire region, which is characteristic of carboxylic acids. Again, with ATR, like we have, there will be less absorbance in here, but you still be able to see some sort of broadening that's happened in this region there for presence of carboxylic acids. So I am not going to specifically tell you to memorize certain frequencies of the functional groups. However, as you're practicing these, it will definitely be helpful to you to be able to pick out a carbonyl, for instance, without looking at the chart, right? Seeing this one big, huge peak at 1700, the only thing that possibly can be is a carbonyl. And then learning about the 3000 line, learning on what's either side of that without having to look up specific values. Probably on an exam, I will give you some numbers for you to have reference from. But honestly, if you've a good way for you to tell if you've practiced this enough is where you can look at a spectrum and figure out, for the most part, what functional group is present without looking at too much else, right? You'll obviously be able to spot an alcohol pretty easily up in here, carbonyl pretty easily in there. Amines are easy to spot. They have very characteristic shapes that we saw before. And then the hybridization of CH bonds will be really easy to spot. So from this point in the textbook, there are plenty of combined problems that have a mass spec and an infrared spectrum to them. You definitely practice up on that sort of stuff. On the exam, there will most likely be at least one combined problem that gives you a mass spec and an infrared spectrum and asks you to draw the structure or something like that. It'll probably give you some information to it, like the molecular formula or something. It's not going to just say, here's two spectra, go to work. In the next chapter, in chapter 13, which we did at the end of last semester, though, there are combined problems that have a mass spec, an IR, and an NMR. It probably would be helpful for you at this point to maybe go in and try some of those. It probably is fair at that point to have just the spectra, because you can be able to piece together an awful lot of information from each of those three spectra, and that's usually what an organic chemist ends up doing. Mass spec, an IR, and an NMR, and through all of that, it's pretty definitive being able to assign a structure from that. So please practice up on this. We'll get plenty of other practice doing this in lab also.